So I'm Fahad Nasir. I'm going to present my work I did at UC Riverside, and the work is published, and the archive number you can see on your right. Okay, so the primary constraint on the redshift of reionization comes from quasi microwave background. In particular, the recent PAC analysis suggests that the reionization is half complete by redshift 7.7. Of course, we know that this redshift have been moved to lower redshifts over the past 2 decades or so. So complementing constraint on the redshift reionization comes from Lyman-α emitters and presence of damping being effects in the quasar spectra, in particular the opacity measurements in the quasar absorption line, in particular the Lyman-α Forest. So for the bulk of modeling, the assumption has been the reionization is complete by redshift 6. However, the purpose of this talk is to convince you that convince you and also explore alternative reionization scenario when the reionization is still happening and the IGM is significantly neutral at these redshifts. Here I've shown you redshift 6 quasar spectra with varying transmission in the Lyman-α highlighted in these rectangles here. So for moderate to very little transmission at the bottom sightline, the bottom sightline in particular includes the 110 megaparsec of edge, a trough. So trough is a segment in the forest which has zero mean flux within uncertainties, of course. So any successful model of reionization has to reproduce the scatter we see from sightline to sightline, and also should be able to reproduce these extreme troughs with reasonable frequency, right? So what if your working assumption is that the reionization is complete by redshift 6? So how you reproduce fluctuation you see in the forest, and your fluctuation would come from the trace neutral hydrogen left after reionization, which would be set by the photoionization rate and the recombination rate. There is significant amount of literature and try to push the limits of these parameters and try to reproduce statistical properties of the forest. So one such model I have shown here, which is shown as dashed blue curve, we call the early reionization model, and the reionization ending around redshift 6. And we contrast that with a model we're calling a late reionization model, the red curve here, where the reionization ending around 5.2-ish. Notice that conveniently, this model is also consistent with the recent constraint we have, Lyman-α emitters and quasar damping vanes. So how does the ionizing background should look like for the two models? So for early reionization on your right and late reionization on your left. So these are ionizing background at redshift 5.6. So for early reionization, the average, especially average mean free path, has to be significantly lower than what we expect, what we observe at redshift 5.2. And this lower mean free path results in intensifying photoionization rate in the vicinity of sources and diminishing in the voids. Now contrast that with the late reionization model, where the fluctuation would come from the neutral islands, and therefore you don't have to assume a significant small mean free path. Notice that in the vicinity regions of these neutral islands, which are shown as white splotches here, this region would be protected from the ionizing radiation, thus producing these shading effect. And this shading effect is very important to reproduce the large fluctuation we see in the forest. Notice also that these cosmic void would be the last region to be ionized in both these models. In addition to fluctuation in the ionizing background, there are also fluctuations in the temperature or temperature field in the intergalactic medium. And the reason is that it's essentially because of the patchiness of the reionization process. And we also include that in our modeling. So we'll obviously look at effective optical depth, cumulative distribution function for the two models. They look very similar, extended, and also broadly consistent but with the observations. So here I've shown you the backend stuff again. And Lyman-α in black curve, Lyman-β is in blue curve. Notice that there's significant transmission in the Lyman-β and coeval Lyman-β. So are we able to reproduce extreme trough in the Lyman alpha, but however have transmission in the Lyman beta for the two models? And yes, we can. So for late ionization model, the transmission in Lyman beta would come from the ionized regions in between these neutral islands. However, because of damping wing, they would offer opacity to Lyman alpha that's producing these extreme troughs. In the case of early ionization model, it is essentially is the diminishing photoionization rate in the cosmic voids will produce these extreme troughs. And however, some transmission in Lyman beta. So we also looked at the trough length, the Comovi length of the troughs in our two models, and in Lyman alpha and also even Lyman beta being into two redshift bands. In general, it looks like they produce very similar distributions. However, there is an axis shown as a bump here in the Lyman beta for intermediate size troughs. So trough size is from 10 to 20 megaparsec over edge, which essentially telling you the sizes of these neutral islands. So Lyman-α Forest is also sensitive to the temperature of the gas, which is responsible for the absorption, right? So this allows us to put, to measure the temperature of the intergalactic medium, and this measurement has been moved to redshift 5.8 lately by Gakwat. Notice these red points here. These are the red points with the latest measurements. They also also agree with the bump we see in the late ionization model achieved at the very end of the reionization process. The uncertainties are quite high here. So, however, future measurements, when we were able to, somebody is able to increase the sample size, we might be able to distinguish between these two models. So how does the large-scale galaxy environment in the vicinity of the Backer troughs look like? So here's a Backer trough again. By implying the narrowband filter on Subaru Hyper subprime cam, shown as a red curve here, which sits in the middle of the Backer trough. George Backer was able to lay out the map of Lyman-α emitters, where colors show the magnitude in the band. Notice the deficit of Lyman-α emitters in the very vicinity of the Backer trough. So if you measure the Lyman-α emitters surface density in 10 megaparsec average analysis, except in the center, you arrive more quantitatively to the plot we see on your left bottom. Notice the dip in the very round of the quasar sightline is essentially telling you we're probing cosmic voids. So here the data points again, and the red curve with the shaded region represents the mean 10th and the 90th percentile of the Lyman-α surface density profile among the 100 most longest extreme troughs in our two models. And we can tell statistically we are probing cosmic voids, essentially the cosmic void that generate the most extreme troughs we see. So what about Lyman-α surface density for the most transmittive sightlines among in the vicinity of transmittive sightlines? So we expect that for early reionization, most of the transmission would come from overdense regions, and for the late reionization model, it will come from lately ionized cosmic voids. And you might expect a tighter correlation. However, we do see a dispersion of such a correlation. This is essentially by including by the complex and contending effects of the photoionization fluctuations, fluctuation in the ionizing background essentially, and temperature fluctuations. However, it seems at first glance that it's difficult to discern between these two reionization scenarios. Having said that, just the possibility of probing the large-scale galaxy environment in the vicinity of the sightline is very exciting and definitely worth further investigation, because it sheds a light on the patching of the reionization process and also on the timing. So late reionization model can explain the observed scatter we see in the Lyman-α Forest. However, it's slightly difficult to discern with a model which is early reionization scenario, however, with a shorter mean peak path. Having said that, thermal history measurements of the intergalactic medium, I mean thermal history and also temperature measurements, would play an important role in distinguishing reionization scenarios. And in addition, direct measurement of the mean free path to the ionizing background also play an important role in distinguishing these two reionization scenarios. So if this late reionization scenario is confirmed, is very exciting time for the community, because the forest has a lot more information and we can use that to probe the tail of the reionization process. Thank you.
All right, thank you. So the time for questions. So there's a question from Tom Toms. What is the meaning of T0 at redshift z equal 5 to 6 in case of the large temperature fluctuations that you showed?
What is the meaning of T0? You mean that slide? So T0 means temperature at the mean density, or this slide. Okay, maybe I think Tom is talking about this slide.
Yeah, okay, great. So
yeah,
the next...
these are temperature measurements of the environment. Essentially, we calculate these semi-analytical models. So we have an ionization field, and we use that to calculate the speed of the ionization front, which tells you what the temperature each patch is going to be ionized, and then it essentially evolves by all atomic processes we know. So these curves are calculated in that manner.
Okay, great. So the next question is from the Melema Garrett. Are your MFP values in comoving or proper megaparsec?
Comoving, megaparsec or edge.
Right. So any more questions from the audience? So I have a quick question. So
right.
Are you with a nice, LA surface density plot?
Right.
Can you show it to us? Yeah, the data points, looks like the decreasing towards 0 while your model are, rising. So why? Yeah, I know that the shade region is allowed, but the trend look opposite.
Oh yeah, because actually these data points are from Becker, so these are the same data points. These data points are from the Beckers, and we are probing cosmic voids. So, and we know that the extinct terms comes in the cosmic voids. That's why they're decreasing.